Hey, this is Paleac, and in this video I'm going to be diving into the fundamentals of sound and the basis for how sound and waveforms all work. I think understanding and having a deep mathematical intuition for how waves and sound propagation and synthesis works is extremely important. I feel like when you have a technical understanding, then you can easily predict exactly what every single knob is going to do on every single synth and how to transform any sound into a sound that you want. And you need to understand how waves interact with each other on a fundamental, deep level. The mathematics in this isn't going to be that intense. It's mostly going to be, we're going to be touching a little bit on some like trig and like pre-calc stuff, but it's all pretty basic. This isn't going to be an extremely rigorous like lecture or anything, but more so I'm going to try to explain intuitions that I've gained over the past 7 years of me making music. My goal is to frame this series of videos as something that, had I seen in my first year or two making music, would bring me to where I am now in terms of understanding the world around me. I think not only does understanding, the fundamentals of sound help with like sound design or mixing or whatever, but I think it also just enhances your quality of life if you give a shit about sound. Being able to notice like room modes in different rooms and how the acoustics of everything interact with each other, or fundamentally understanding why certain instruments or sounds have specific timbres, and having a deep fundamental understanding of the nature of sound gives you a more fundamental direct understanding of the universe around us, because sound is one of, if not the most direct sense that we have to our surroundings. And ultimately, it's all like pretty fucking cool. So I think whether or not you gain something extremely helpful for making crazy dubstep basses or whatever your goals are, I think the appreciation that you can gain through having a fundamental understanding of all of this is one of the greatest things that life has to offer, at least in my experience and in my opinion. So we're going to talk a bit about the fundamentals of waves, FFT, frequency modulation, phase modulation, wavetable synthesis, distortion, comb filtering, and how all of these different things directly relate to each other, and how you can build up intuitions for how all of these things work from the basic axiomatic components of sound. Because while all of these individual things can be and can sound extremely complex, they all emerge from simple rules. Sound is just emergent complexity arising from very simple fundamental truths of the universe and mathematics. So to reiterate, the point of this video is to give you an intuition for and to show you some brief visual or mathematical proofs for how sound works. If you want to learn this more rigorously and deeply, then I found this really, really great public course on the fundamentals of sound and acoustics. This is an incredible resource. I read through the whole entire thing in like an hour and a half. Granted, I already know most of it, but it still gave me some really, really great insights and intuitions for a lot of stuff that I haven't considered before. So I would also recommend checking this out. I'll put this in the description. Consider that this waveform is simply instructions for how you want your speaker to move. When you press play, this information is going to be sent out of your master and through your DAC, your digital audio converter, and this is going to tell your speakers to move. This says that when I'm at a peak here, I want the speaker to push out, and when I'm at a trough or a minimum, I want the speaker to pull inwards. And by doing that, it's going to create pressure waves in the air, which then will travel through your room and reach your ears, and you'll hear it. That's fundamentally all that sound is. Sound is just wiggly air. And we use signals and waveforms and this, this visual representation of a waveform to describe how that air wiggles. So if you think about what I'm doing right now is, right now I'm speaking, right? Commanding my vocal cords to vibrate. And then my vocal cords will vibrate and it'll oscillate and then be projected out of my mouth. And based on the shape of my mouth, I'm able to like shape the wave in different ways, which then can carry different semantic information. And then that goes out and then hits my microphone. And my microphone has a membrane that is very resonant and will wiggle very, very well in response to the air, because the air is just pushing against it and then pulling against it really, really quickly. This microphone is then attached to a magnet, and then that magnet can read the electrical signal of how close the microphone membrane gets close to it and further away. And then that microphone is wiggling in the exact same way that the sound is coming out of my mouth. And then that information is then written down, saved over the internet, sent to your speakers, and then your speakers are wiggling in the exact same way. will emit that sound, and the air, will oscillate and wiggle and then reach your eardrum. And then your eardrum will wiggle in the exact same way as well, because your eardrum is just another transducer, just like your speaker, just like your microphone, just like your vocal cords. Everything in sound, everything that can capture energy in sound and transmit it are all just considered different types of transducers. And then from your eardrum, it is then connected to your auditory nervous system within your brain, converts these pressure waves into electrochemical signals for your brain to then process and interpret. And then if you were to then explain all of this to someone else, you then take these concepts and ideas that have been, transformed from sound into some sort of like neural net, synaptic connection, crazy biological bullshit in your brain. Then you speak and then vibrate your vocal cords and use another transducer to emit sound, which then goes into someone else's eardrums, and then the information spreads. It's all just information traveling from one point to another through different mediums, and we're using signals to do so. Now, while we represent sound as these waveforms on a horizontal and vertical axis, that goes up and down, it's wiggling up and down, sound does not travel that way. It doesn't go up and down as it's going through. Rather, it's compressing and expanding, because the air itself is, like millions and billions of little air particles, right? Little oxygen, O2, carbon dioxide, whatever, all those little particles floating around the room. And when you push against it, then they will push against their neighbors and it'll just keep moving, similar to like a Newton's cradle, right? And that will create compressions of the air pressure at that point. So it's more similar to like a slinky. I have a slinky here. How cool is that? So, like a wave like this would be going, up and down, right? Or like side to side or whatever. But if I were to move it up and down and compress the wave and expand it, this is more so what air is doing. However, it's on like a three-dimensional scale, and it expands outwards in all directions. So it's kind of difficult for the human brain to conceptualize and understand that, considering we can't actually see it. So that's why it is most easily expressed as a two-dimensional waveform. Now, this two-dimensional waveform, the x-axis is time, and the y-axis is the pressure. It is centered around the ambient pressure amount in the room, right? So every room has some amount of air pressure in it. So we normalize that to say that ambient amount is 0. And then when there's more than that, then it's above it. And when there's less than that, then it's below it. So I found a cool little video here that gives a little demonstration of how sound works. Here's a guy clapping, right? You can see it explodes outwards in compression waves, right? So because sound is the study of how air will oscillate or vibrate, it is worth it to understand just a little bit about the foundational physics of how things oscillate, right? A lot of things oscillate. It's a fundamental aspect of mathematics and the universe. So if you have, for instance, a spring, right, that's, doing this little thing, the further it gets away from the median point, the more force is going to be applied upwards. However, it's going to have the momentum of it already going down. So it's going to go down, it passes the middle point, and then there's going to be force applied upwards up from the spring that'll slow it down, and then when it reaches its bottom, right, after the force has been applied enough, it'll reverse directions, and then the force will switch, and then it'll keep going up a little bit from the momentum it had previously, and it'll just do this endlessly over and over again until like friction or, some damping constant of the spring, it ends up slowing down, right? It does this and then eventually it stops. The same thing applies to pretty much every single phenomenon regarding sound. So if you have let's say like a tuning fork or something, and you hit a tuning fork, right, which is like a little like a metal rod, the molecules in that, you can imagine, are traveling through it, right, through a compression wave, and then they hit the outer edge of the tuning fork, which causes it to bulge out just a tiny bit, which creates like a compression wave in the air, and then the tuning fork molecules will then reflect off of that surface, that boundary, the boundary of the tuning fork, and then go to the other side and then reflect off of that, and it'll just keep going back and forth, and then that creates, oscillations. So we also need to understand sine waves, right? Because they're extremely foundational to not just music, but mathematics in general. They appear everywhere. So, a sine wave is what happens if you're tracing like the x or y axis of a circle as it goes around it. So a sine wave is simply a function that you input some value, and as time progresses, it oscillates in this pattern. So it starts off at 0. If the function sine of 0 equals 0, right? And then as you increase the value what's within the sine function. It'll increase up to some maximum amplitude, which is 1, and then it'll decrease back down to 0, go down to -1, and then increase, and then the pattern resets. So it is a repeating function. It's oscillating and repetitive. The period is described as, the point from when it repeats. So crest to crest is the period, or this point to this point, or trough to trough. This is obviously the crest, this is the trough, etc. We describe the amplitude as the value between 0 and the maximum, or 0 and the minimum, because it's generally going to be reflective on both the positive and negative axis. The frequency is going to be how fast is this occurring? What is the time in which this happens? So notice frequency is determined by this length on the x-axis, but so is wavelength. And wavelength and frequency are intrinsically dependent on each other. They're practically equal. If you have some frequency, you're going to have some other set wavelength. All right, so now we are looking at Desmos, which is a little graphing calculator, and this is the function of a sine wave right up here. So you characterize a sine wave. You can describe any sine wave with just these basic components. There's an amplitude A, which as you vary A, makes it bigger or smaller. This is corresponding to loudness. If this is what I'm telling my speaker to do and I'm pushing it out even further, then there will be even higher amounts of air pressure or lower amounts of air pressure depending on the amplitude of this, which will then, pulse your ear further in or further out, which will create larger waves that go within, your cochlea and all that stuff. So amplitude controls this guy. This is multiplied by 2 pi. 2 pi just works here as a constant to make it so that if your frequency is 1, then the cycle repeats every 1 second. That's all that is. So you can ignore the 2 pi. This is multiplied by f and by x. X here is our time, right? So this is a function of time. I guess you could say it's t, but it's because, we're graphing on an x and y axis, we're saying this is x. So this is staying the same, but we can vary f. And if we increase f, then that means that this whole function is going to be increasing even faster, and it's going to resolve faster, right? So if I, have it set to times 10, then this is going to be moving 10 times per second, whereas, if it's at 1, it's moving 1 time per second. This last little guy here, this is the phase of the wave. So as you can see, we start off at 0, right? If I increase this value here, and we're set at 0, that means this term is going to go to 0, and then we're going to be dependent on only this term, which means this point here will be shifting, right? So as I increase phase, it all shifts, and this repeats every 2 pi radians, right? So 6.28, whatever, that's 2 pi. Perceptually, we can hear frequency, right? Something sounds higher in frequency or lower depending on how fast it's moving. You don't really hear phase, at least by itself. Phase is something that's dependent on something else. So if someone is saying, hey, what's the phase of this sine wave? And there's a sine wave playing, that is a useless question and doesn't make any sense, because the sine wave is constantly changing in phase because the frequency, because it's moving, right, over time. What really matters is the relative phase between two waves. So if I have another wave over here, right, and I have two waves, and if I increase the phase of this wave, they are now offset from each other. And now you could say, what is the phase difference of these two waves that are playing side by side? Because they're going to constantly, till the end of time, have this difference, right? Assuming they're the same frequency. If they are of a different frequency, then you're going to see that the phase difference, or where they are in their cycle, is going to be constantly changing throughout the entire thing. We can also take a look at what does it look like when we sum these together, right? So if I enable this graph here, this little green guy, let's multiply this by a larger value so that you can see it. This is what happens when you're adding a 1.2 hertz wave with a 1 hertz wave, because as you can see, there are points where they're adding together, right? You add these two values together, and then it's going to give you a big value. And then there are other points over here where they're practically opposites in terms of phase. The phase is 180 degrees, or 1 pi, or just 50% out of phase from each other, meaning that they're going to be almost entirely negative from each other. So if you play this wave, you're going to get this beating, this pulsing effect, which is the result of these being slightly off, right? So, and then as you increase the frequency, it gets more and more complex, right? While this might look pretty complex, this is just the addition of two waves together. And you can keep on adding waves over and over again, and it's going to keep getting more and more complex as we add more waves. However, it is still going to be the result of just adding simple sine waves together. Now, some important things to note regarding phase and frequency. Phase and frequency are inherently linked together. So if you were to describe the phase of a wave, typically this value is used to describe the relative phase of this wave at some specific time point or in relation to another wave of the same frequency, because frequency also changes the phase. If you were to say, what is the phase at time t equals 1, right? After 1 second, what is the phase of this wave? It's like a little bit less than 0. The cycle repeats right here, and then, it's a little bit over here. But that's dependent on frequency. If I make the frequency something else, then it's a totally different value, right? So the phase at any particular point in time is dependent on both frequency and phase. It's just that if frequency is 0, then it's determined solely by phase. Now, what happens if we change phase over time? This little value here, right? So this is gonna be important later in regards to frequency modulation and phase modulation synthesis. But if you change phase over time, right? If I drag the slider, we can see that this wave is moving. If I multiply this phase by x, then as I increase, notice that now, instead of just shifting, this is now instead increasing the frequency of the wave instead. So the rate at which you change phase is frequency. No, I'm sorry. The rate at which everything inside this parentheses changes is frequency. And then the point within a wave where it is in its cycle at some particular point in time is phase. Frequency and phase are two aspects of the entire sine function itself. Frequency isn't determined solely by this f here, and phase isn't solely determined by this phase here. Typically it will be, because you're usually not going to be changing and modulating phase, but you can see that this is the case in a lot of different situations. So if we look at Doppler shift, for instance. So let's say you are an observer and there is a source some distance away from you, right? The distance that you are from that wave determines what the phase is of the wave that hits you, right? If the source is not moving and it plays a sound, it plays a sine wave, that sine wave is going to keep hitting you with some phase, right? Now, if you get closer, as you move towards it, you're changing your distance. As you change your distance over time, you're changing what the phase is of it over time. And then it's going to start hitting you faster. The distance is the phase in this physical example. And so the phase change creates frequency change. So by the ambulance in this example approaching you really quickly, you're going to hear a shift in frequency. Though the actual emitting frequency of the siren of the ambulance doesn't change at all. What's changing is the distance between you and it, which is changing the relative phase really quickly, which changes the frequency. So we've been mathematically describing how sine waves work. They don't really disturb each other. They pass through each other, So, if there's like a pressure wave meets another pressure wave, they don't like bounce off of each other, they go through each other. Similar again to like Newton's cradle. When you have multiple pressure waves, meeting together or being, sent out at the same time, the amplitudes will add together. You can get both constructive and destructive interference. Now, from these very basic principles regarding how waves work and just like simple arithmetic and multiplication and how these functions work, you can then extrapolate upon that and then prove upon that and create foundations and foundations of mathematics regarding signal processing that all applies to sound. So this is why mathematics and signal processing is so important. I'll link a video to a 3 blue 1 brown video on how the Fourier transformation was derived. But essentially, we can see how, if we have a bunch of different frequencies, right, and we add them all together. So like right here, I have this function is adding 4 different waves together with like some arbitrary frequency assigned, right? If I start adding them together, I get kind of a complex wave, and then it gets more and more complex. However, if I set most of the terms to 0, there's just a sine wave at the end of the day, right? Now, you can imagine that if someone has this wave, they could theoretically decompose it down into the original 4 waves. And that's what the Fourier transformation is, and FFT. So homie Joseph Fourier, mathematician, physicist guy, he discovered, hey, I can represent actually any signal, any periodic signal as a sum of a bunch of different sine waves with varying amplitudes, frequencies, and phases. It's all sine waves. Now, let's just assume that is true. I mean, intuitively, it makes sense, right? Just given that you can construct very complicated waves just by adding sine waves, the idea that you can deconstruct any complicated wave with sine waves using math, I think that makes sense. Another consequence of this is that any wave that is periodic, meaning the entirety of the wave resets with some frequency, all of the sine waves that compose it are going to be harmonics or harmonically related, which means that the frequency of all the sine waves are going to be some integer multiple of the lowest frequency. So if the first frequency is 100, it's going to be composed only of frequencies that are at 200, 300, 400, 500, and so on, right? So I think the easiest way to understand why that has to be the case is by just adding a couple sine waves together and trying to see when can you get them to line up, right? So we have a 1 hertz signal right here. So this cycle resets over here. What I want to do is I want to add another signal that also resets right here. Right now it doesn't reset right here. It's crossing the 0 axis, but I want this point here to match up, right? And so you'll notice as I adjust the frequency is set to 1, they're lined up perfectly, right? I'm just adding 2 sine waves with the same frequency. As I increase the frequency, the next time that is going to line up where there's another rising little peak here when the phase resets is going to be at 2 hertz. There's no other time between 1 hertz and 2 hertz until there. And then we can do it all over again up until 3, right? And then so on and so forth. Now, there are some other parts that are harmonically related. For instance, at 1.5 hertz, you'll see that it matches here when it's going down. But if we look all the way to the second time that this wave resets of the fundamental, we can see that the larger wave plays through twice, and then the bigger wave plays through 3 times, right? So there's going to be a 3-to-2 ratio right here. So these are still harmonically related. In fact, this is implying that there is a sine wave fundamental underneath both of these that spans the distance of 2, right? So from this, you understand all waves are composed of sine waves, and all periodic waves that repeat with some frequency are composed of harmonics. They're harmonically related. Now, something important to keep in mind is that in the FFT equation, it's an equation. It means it is equals to. The wave is equal to the sum of all of its parts. It is not that by adding sine waves together, you can create an approximation of the wave. It is that you are creating the same wave. You can take my voice, recreate it with sine waves with an FFT algorithm, and then it will perfectly cancel out, and there's no difference whatsoever between the data that my voice vibrating against this microphone is creating and a recreation of that using sine waves artificially. It fundamentally is the exact same thing. So if we look at, for instance, a square wave, which is one of the fundamental basic shapes within synthesis, right? You can see f of t equals this big old thing, and essentially what this is saying is composed of odd harmonics, and the amplitude of each of the waves varies depending on those harmonics. So like the very first harmonic is going to be amplitude of 1, the second one is going to be an amplitude of 1/3, and then it's going to be the third harmonic, and then the third one is going to be the fifth harmonic, and it's going to have an amplitude of 1/5, and so on. And by adding all of these together, you get closer and closer approximations of a square wave, right? Now, this is extremely important for subtractive synthesis, because no one in their right mind wants to actually, with a synthesizer, add hundreds of sine waves together to recreate it, unless you're trying to build an additive synth. It isn't very feasible, especially when synthesizers were first being made. So what people do instead was they would just say, hey, computer, just create a square wave. This is an extremely simple thing to graph or to create with a computer. It's simply just a -1, and then it flips up to a +1, and then just does that. And then you just try to output that with a speaker. And then guess what? By doing that, you are getting all of these sine waves because they're equal to each other. So a sawtooth wave, which just ramps all the way down and then jumps back up and ramps all the way back down, that's extremely easy to create a signal of. You don't have to add up all the harmonics. However, by outputting it through a speaker, it's going to output harmonics as well, which you can then filter and remove and take away and do more mathematics on. So I have a sine wave here. And by slowly adding harmonics to it, right, there's 2 waves added, 3, 4, it starts to become more and more square. And then you end up getting a square wave, or a close approximation to it. You can also, for instance, with like serum or something, you can choose this guy to be basic shapes, and then output a square wave. And it's almost the same thing, pretty much. And this is just saying, hey, I want computer, move my speaker out, and then in, and then out and in. Just do that really quickly, and then you get that. Now if you make it a saw wave, you get a different sound, right? This is the fundamentals of synthesis. So let's say if you have a saw wave and you want to filter out the high end. I find something important to think about is what is going to happen to the sound, like on an oscilloscope, what'll happen? Well, by applying a low pass filter, you're kind of removing all the high frequencies, which in effect is like almost a smoothing function. You're kind of smoothing and making every single value of the wave get closer to the nearby other values, right? Which you can kind of see how that happens. And that's fundamentally how subtractive synthesis works. It's really cheap and easy to use some like basic shapes, right? And then you can apply different like mathematical algorithms and effects and stuff to create cool sounds. If you record the output of this serum, right? We see the saw wave here, we're gonna see a saw wave here, and then we record the output out. You zoom in over here, and then it's the same thing. These are just the instructions that just end up going out to your speaker. It's all just instructions. It's just pushing and pulling and air wiggling. So let's say I go back to my little song here, right? And instead of actually playing it out like normal, I can simply highlight a section, the size of this wave over here, right? And then I can just duplicate the section over and 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 over again. Right? And what is this gonna do to the song, right? What is this gonna sound like? Well, if you think about it, this is just a repeating wave of a fixed length or wavelength, which means frequency, and it just repeats over and over again. So we're gonna get a sound that has that is full of harmonics. Would you look at that? So this is essentially how wavetable synthesis works, in which you would import a whole sample and then comb through little chunks of that sample that are repeating really, really fast. So if I were to take a sampler, so I can import my sample of my song into the sampler, right? And I can set this to loop, and then I can change the length of the loop size. And then you can simply comb through this. And it's playing at the same frequency the entire time, but each part of it has a different timbre. And if you were to, like, for instance, slowly comb through this, right, go all the way through, okay, so let's talk about frequency and phase modulation. So I have an operator which is playing a sine wave at 100 hertz, right? I can set the frequency over here. And so you can see on the oscilloscope, and you can see spectrally the fundamental and then all the harmonics above it that we'll be adding. So if I take an LFO, which an LFO is a low frequency oscillator. So this is an oscillator in the same way that operator is outputting an oscillator that tells your speakers to move. But instead of this telling your speakers to move, we can tell this to modulate different parameters, right? So this is the same mathematical type of function that we're using to make sound, but this isn't going to your DAC. This is instead controlling parameters for the thing that's going to your DAC. So if I take this LFO and I map it to frequency, it's going to start sweeping 1 time per second. You look at this oscilloscope and you can see that the waveform is compressing, or the frequency is increasing, right? Or the wavelength is shortening, and then it's expanding all the way back out, right? And if I lower the depth, it's a little bit less extreme, and then if I increase the rate, suddenly you hear all these overtones all the way above it, right? Once it's playing at a faster rate. And not only that, but the waveform is now, instead of being like one obvious sine wave that's compressing and expanding, it's now this much more complex thing. So what's happened is, by using this LFO to tell the oscillator to speed up and then slow down really, really quickly, it's speeding up and slowing down so fast that that's happening within one single wave cycle, which is going to change the shape of the wave, which creates harmonics, because any wave that's periodic is composed of harmonics, right? Now, these harmonics aren't completely in tune, because this is a 40 hertz wave and this is a 100 hertz wave. So this LFO isn't resetting at the same time that this waveform is resetting, right? So it's going to sound unstable. But if I multiply this rate by 10, and I set this to 10, so this is at 100, is a little bit more stable, but still not quite. Now you'll notice, no matter, by changing the depth, I'm changing the stability of the waveform, right? Because there's like this beating, you know? Right? You hear that beating? Even though this is 100 hertz and this is 100 hertz, it's not completely harmonic. This is playing 100 hertz and this LFO is playing 100 hertz. They aren't quite repeating at the same time, because this LFO is changing the phase at the same time. When it speeds up, the phase is changing much quicker, right? Because that's changing the frequency at which the phase is going through its waveform. When the period has reset on this wave, the phase is actually going to be at a varying point depending on the amplitude or the depth of this modulator, right? So if I make it go way faster, then that's going to have a drastic change on what the phase will be at the end of its waveform, depending on the depth and the amplitude. And if the phase isn't completely reset by the end of its waveform, that means that that waveform isn't periodic within that one cycle. It's going to take longer, right? So if the phase is like 1/4 off by the time the cycle has reset, that means actually it's going to take 4 cycles to 100% reset, which means that that waveform will actually be composed of harmonics of something 4 times slower, right? So that's why the amplitude of this LFO controls the stability or the tuning of the harmonics relative to each other, because both the amplitude and the rate of the LFO control where the phase is at the end of its cycle. Right? So you're getting beating. This is the problem with frequency modulation. It's really difficult to get both the modulator and the carrier to sound in tune, because you have to vary and work with the amplitude as well of the modulator, right? Now, this is where phase modulation comes in. So most FM synths actually use phase modulation. So Operator doesn't use frequency modulation normally. That's why I had to do this little LFO hack. What it uses instead is phase modulation. So it has another oscillator controlling the phase, which, if you change the phase, you're changing the frequency, right? So phase modulation is another way to change frequency. Now, why would you do that? Well, if we listen here, I'm going to modulate this 100 hertz wave with another 100 hertz wave. And you notice something? It's completely stable. It's completely in tune, no matter what this amplitude is. Now, the reason why it's in tune is because by directly modulating the phase, if your modulator and your carrier are harmonically related, so this, these both have the same frequency, that means by the time the main carrier frequency has reset, the phase will also completely reset every single time, because they're mathematically in tune, which means the waveform will be in tune. The phase will always be the same at the end of it. And so it'll stay 100 hertz as the fundamental and be composed of harmonics above it, right? Now the question is, how exactly does phase modulation change the frequency? Because the wave that you're using to modulate the phase isn't going to create the exact same wave modulating the frequency. They're actually going to be a little bit different. So here we got our trusty MS Paint. So as I said before, the rate at which you change phase is frequency, right? And so I'm going to be talking about the derivative, which is something from like calculus, but it's pretty simple in this context. So if we have a sine wave, right, and this is what we're using to modulate the phase of something, what you want to do is you want to look at the rate at every single point, right? So right here, it's increasing pretty rapidly, right? This is the most it's going to be increasing at any point. So we'll call this 1. And then over here, the rate is 0. It's not increasing or decreasing. And so we'll make this 0. And then over here, it's decreasing. And this will be down here. And then here, it'll be like that. And so it'll be like that. And then vice versa. And so on and so forth. And then what you get here is you get another sine wave, but the phase is just a little bit offset. This is another reason why sine waves are so like mathematically powerful and intrinsic to the universe. The derivative, or the rate at which the sine wave changes, is just another sine wave. So the second derivative, or the rate at which the rate changes, is just another sine wave, and it just keeps going. It's just that the phase is offset. So if you think back to this little example that I used before with simple harmonic motion, the position of the spring is going up and down with a sine wave, which means that the velocity, or how fast or the rate it's going, is another sine wave that's offset from that. And then the acceleration of that, or the force that's being applied to it, right, is going in the opposite direction, right? When it's all the way down, there's a force being applied all the way up, and vice versa. And that just keeps going for every single rate of change for it. It's just derivatives on derivatives on derivatives of sine waves at varying phases. This is important here because let's say, let's make, here, I'm going to make this times 1/10. Let's make this move 5 times per second or so, right? Though we're modulating the phase, the frequency is now being modulated with another sine wave, 5 times per second, right? And this is because the rate at which the sine wave moves is changing. What happens if I use a triangle wave? Well, let's think about this for a second. And honestly, I advise you like pause the video and think about what it would sound like yourself. A triangle wave increases, right? And then it instantaneously decreases. So it's going to have a high slope or a high derivative, and then immediately a low one. And so it's actually going to create a square wave LFO controlling the frequency. And you can see that here. Now what happens if we have this set to a sawtooth wave or square wave? Let's use a square wave. It's at a maximum value and the slope is unchanging, and then it instantaneously drops down and then the slope is unchanging. And so it's gonna not actually change anything except for that little instantaneous drop down. There's probably gonna be like some click or something, right? There we go. And you'll notice that even though I'm changing frequency here, the fundamental is always there and never actually gets modulated. The frequency doesn't get modulated. It's more so we're like audio rate modulating with this little click that's happening from the instantaneous jump down, which is weird. And then the same thing actually applies to a sawtooth wave. So a sawtooth wave is just going all the way down and then instantaneously jumps back up and then goes all the way down. So it does have a slope. So this is going to change the pitch of the fundamental, but it's going to be constant the entire time. So the amplitude of the saw wave changes the fundamental. So it's pretty much the same thing as square wave phase modulation, but the amplitude and the frequency both change the fundamental. Now, we're going to talk a bit about comb filtering, and this is pretty important to understand. And when you fundamentally understand it, I think some of the insights that you can gain from understanding comb filtering can extend to other areas, such as like distortion or even like wavetable synthesis and stuff. So, what is comb filtering? Comb filtering is the effect that you get when you delay a signal by a very, very short amount of time, such that that amount of time is about a wave cycle or half of a wave cycle, which will end up offsetting the phase of certain frequencies. So if I delay something by half of a 100 hertz wave cycle, which 100 hertz repeats every 10 milliseconds, so half of that would be 5 milliseconds. If I have this white noise here, and I delay it by 5 milliseconds and mix it with a 50% dry wet, what's going to happen is all of the frequencies that are present at 100 hertz are going to completely cancel out because 100 hertz has now been set out of phase with its copy, right? Not only that though, but you also cancel out harmonics above it. So we can see here, we have 100 hertz that gets removed, then we have 300 hertz, and then 500, and then 700, and then 900. So all of the odd harmonics get canceled out. So for instance, if we, just like understand, okay, what is a square wave and what is a sawtooth wave? A square wave looks like this. It is symmetric on the negative and positive axis down the middle, right? So if you mix a square wave with another square wave that's been offset 180 degrees, you're going to get nothing. So we can take two waves. So it sounds like this. And then I set the phase of one to be at 180 and the other one at 0. You're going to get nothing or almost nothing at another sum. I don't know why that's the case. You should hear nothing though. Now, what happens if you do this with a sawtooth wave? Well, sawtooth wave actually isn't symmetric down the middle. While yes, there appears to be some symmetry along the middle, I want the second half to be a negative copy of the first half, right? So like in the beginning, this is +1, and then right in the middle, this is 0. If this were to be negatively symmetric along the middle, then this should be -1, right? So like here, every single point 180 degrees away is a negative copy of the other one. And so if you mix these two signals together, some of the frequency content goes away, but not all of it. Now, square waves contain only odd harmonics. So that makes sense considering if you're mixing in a signal with another signal with a copy of itself that's 180 degrees out of phase or delayed in time such as 180 degrees out of phase, then it makes sense that all of it will cancel out because it's all odd harmonics, and that's effectively a comb filter. A sawtooth wave is composed of all harmonics, including even ones. So it makes sense it's not going to be symmetric down the middle. In fact, all waves, relative to some fundamental, all harmonics are going to be negatively symmetric along that axis. Now, this is pretty obvious when you actually inspect the waveform. So you can see here, if you have the fundamental at the halfway point, it is negatively symmetric, right? If you have an even function, or 2 times that frequency, it's just a copy of itself right here. So if you were to delay and layer this with something 50% out of phase, you're just going to double it in volume, while the fundamental will completely cancel out. Now this applies for everything. So if we multiply the fundamental by 3, right, you can see right here, it's negative versus here it's positive. So it's a negative inversion. And then, if I was to multiply that by 4, then it's the same thing again. Right here, down the middle, it's just a copy again. So this is why comb filtering will remove odd harmonics. So now that we understand that, let's touch just a little bit more on distortion. Distortion is simply, I guess, when you distort the shape of a wave, either electronically or through other mediums. So if you are driving like a loudspeaker very, very hard, there are going to be nonlinearities in the speaker that end up distorting the wave. So if you keep increasing amplitude and you're trying to push the speaker cones further than they really can, there's going to be some tension as a result of the cone, having spring-like simple harmonic properties. They're going to add extra force the further out it goes, and when you add extra force on a sine wave, you're going to start distorting and shaping the sine wave. And so this is why if you overdrive a speaker, it ends up distorting in the same way that you would apply a saturator to a sine wave. So if I have a sine wave here, right, let's say it's on digital clip, this is simply saying As I increase the drive, I'm just increasing the volume beforehand, and any part of the signal that the amplitude goes higher than this value here, clip it completely. Shape the wave such that it just cuts the top off, right? And you'll see this turns into a square wave the more and more I clip it. Right? You can think of this as either shaping the wave or it's adding odd harmonics to it. They're both fundamentally the same because waves are sine wave components, right? Now, if you use analog clip, what this is simply saying is the closer that you get to that boundary, start to shape it more, but never hard clip it. It just constantly gets closer and closer to that square shape. And so you see that this is more curved. Now, there are also different types of saturator presets that you can use that all have different characteristics and sounds in the way that they bend and shape the wave as you increase the drive. Now, for the most part, this all adds odd harmonics. So how might you add even harmonics to something? Now, I encourage you to think about that for a second. Really, like, just pause the video and think, how would I add even harmonics using a saturator? And the answer to that is to use a saturation curve that is not negatively symmetric. So it could be either positively symmetric or completely asymmetric, and then it's going to end up introducing even harmonics. You can see here, we got our even harmonics. What's also interesting is this sinoid fold. It folds over and turns into more sine waves as you increase the gain. So I'm increasing the gain, it starts to flatten out, similar to the analog clip. And then it ends up coming back down and then folding into another thing. So if I have a sine wave, it folds over and turns into more sine waves. And this ends up sounding really similar to frequency modulation synthesis because there are smaller cycles now contained within the larger one, which is what you get if you speed up and slow down the waveform really quickly. If I were to use, for instance, wave shaper here, I could shape it so that this is no longer negatively symmetric. And you'll see here that our fundamental, which is at about 60 hertz, we now have a second harmonic and a third. Whereas if we go back to this, we have our little 68 hertz, and then we have our third harmonic over there. So this is a lot more obvious, for instance, if you were to use, let's say, roar. Right here, you know, almost all the saturation curves are symmetric, right? Which are just going to create odd harmonics. Right? However, if I were to change the bias over here and increase the bias a little bit, right? The bias changes like where is the center point, I suppose. If the bias is a little bit offset, this is going to create an asymmetry. So the bias is 0, we have odd harmonics. I add bias, now we have even harmonics. If you were to use a half-wave rectifier preset, which just means, I guess, it's just zeroing out everything that's negative. You're getting even harmonics, which has its own tonal characteristics, and that's something that you can learn to hear and then play with. And if you think to yourself, I want this bass to have more even harmonics, then you can introduce asymmetric nonlinear distortion. So here we can have like this low bass. And fill it with even harmonics. Okay, so I think that's plenty of information. There's a few more things we can like dive into, like ring modulation and amplitude modulation, which are just other ways that you can shape a wave and then add other harmonics by modulating different waves together. But at the end of the day, it's all pretty intuitive to understand when you realize that you just have to examine the shape of the wave itself and how that ends up creating harmonics within that one cycle of a waveform. When you have this framework of understanding sounds as their own actual waveforms, everything becomes a lot more intuitive. And I also recommend trying to visualize in your head what the sound would look like in space. So imagine actual compression waves of air coming towards you. So if there's, some complex wave that like speeds up and slows down a lot within a waveform, what would that look like in the air, with like different like gaps in areas of high pressure and low pressure, and how that's going to make your ear shake. Envisioning all of that as it happens, I've found to give me like just really interesting subjective qualitative insights almost to as to how to understand sounds that are happening. So yeah, let me know if you enjoyed the video. I hope I was able to convey some of these like insights that I've had. I know some of the information was probably extremely obvious or you already knew it, and maybe some of it was a little bit less obvious, but it's probably important to touch on everything, and especially because everything kind of relates to everything else, right? Everything in sound is based on these few really basic like facts regarding, like phase and frequency and amplitude regarding waveforms. And you have to understand all of that intuitively and then suddenly start seeing that appearing in everywhere. So, we had understandings regarding phase and how that applies to comb filters and how that applies to triangle waves and square waves. And then suddenly we're having insights and revelations on how distortion works. It's all intrinsically related because it's all just waves. Everything's just waves, man. And if you really enjoyed this video, then consider supporting me on Patreon. I have some Patreon exclusive videos on here, and I give away sound design racks, and you can give me money, and then I'll be happy. And then what would probably make me more happy than that even would be just go listen to my music. That would be so cool of you. So yeah, hope that was useful. Take care.